Okay, so good evening, ladies and gentlemen. I'm Peter Haynes. I'm the head of the Applied Maths and Theoretical Physics Department, DAMTP, and I'd like to welcome you to the 8th Andrew Chamblin Memorial Lecture. There's now a substantial kind of tradition of this lecture. Previous lecturers have included Stephen Hawking and Roger Penrose. Last year we had a very interesting lecture from Frank Close, who basically gave us his predictions for the Nobel Prize for the Higgs boson, and that was duly awarded in October. So that was kind of interesting. And this year we're very pleased to have Professor Michael Green as the 8th lecturer. So before I introduce Professor Green, I just wanted to say a few words about Andrew Chamblin, in whose memory this series of lectures has been established. So Andrew was a Texan who came to the UK in the early 1990s, and he worked first with Roger Penrose at Oxford, and then he came to Cambridge as a PhD student to work with Gary Gibbons and Stephen Hawking in our department. He was a student at St John's, and then he moved later to Pembroke as a Draper's Research Fellow. And sadly, his brief but very productive research career was ended by his unexpected death at the age of 36 in Louisville, Kentucky, where he was an assistant professor in physics. So after his death, Andrew's many friends and collaborators, both in DAMTP in Cambridge and elsewhere, have established a fund to allow this series of lectures in perpetuity in his memory. And the idea is to promote the broad area of science in which Andrew was interested in, and my impression is that he was interested in many things. So we in DAMTP are very pleased to take responsibility for organising these lectures, and we regard it as one of the important sort of occasions in our calendar each year. Andrew's parents have sometimes been with us. I think they can't be with us today, but they've commissioned a striking bust of Andrew, which you can see if you come to DAMTP. So I'd now like to move on to introducing our speaker this year. So that's Professor Michael Green, who's Emeritus Lucasian Professor here in Cambridge, and he's a much valued colleague of all of us in DAMTP. So Professor Green was one of the founders of string theory, which is generally regarded as the most successful candidate to date to unify quantum theory and general relativity, the two fundamental physical theories of the early 20th century, and thereby to allow formulation of a consistent quantum theory of gravity. Michael Green's leading role over many years in developing this theory has been acknowledged by many awards and prizes, including the Heinemann Prize of the American Physical Society and the Dirac Medal of the Institute of Physics, and most recently the 2014 Fundamental Physics Prize. So, Michael, very pleased to have you here today as the 8th Andrew Chamblin Lecture. Your title is going to be The Pointless Universe, so welcome, Michael.
Thank you. I'd like to begin by thanking the organisers for inviting me to give this lecture. It's a great honour to pay tribute to Andrew Chamblin, who I didn't know well, but the brief interactions we had with each other impressed me a great deal, and it was a tragedy that he died so young. So this lecture is going to be aimed at an audience which I hope are non-experts, and I hope they are keen to learn and quick to learn, because I'm going to cover a lot of ground. Let me begin by just pointing out this logo. So the logo summarizes every aspect of this lecture. The logo symbolizes Newton's apple, so it's something to do with gravity. It's an apple. Newton was, of course, in Cambridge, so that's the Cambridge aspect of it. And the apple is made of string, and that's meant to indicate that I'm going to be talking about string theory, which has something to do with gravity. But what I'm going to have to do is set the scene. It's very difficult to give a 1-hour lecture on string theory and hope to teach anyone anything. So that's not the aim of this lecture. The aim of the lecture is to convey the fact that string theory is an exciting subject. It's by no means finished, and in fact, some of the greatest excitement is around what has been taking place in recent years, and it looks as if this is going to keep going for a long time. So if you're here to hear a final, finished story, you're going to be sadly disappointed. But I hope that you will get something out of the talk anyway. So I'm going to begin by giving a brief, well, a brief background to the kind of physics that is encompassed in string theory. And to do that, I thought I'd first talk to, since most of you are not practicing theoretical physicists, I thought I would just describe in the opening few minutes some of the qualities that are needed in theoretical physics or physics in general. And in particular, there's no better place to start than with Isaac Newton. So this is the statue in Trinity College of Newton. And this, in some sense, summarizes 3 distinct scientific qualities which go into the advances in physics. Firstly, if you look at what he's doing, he's holding a prism, and that's an indication that Newton was an experimental scientist. He was a brilliant experimental scientist who revolutionized the subject of optics, in particular, by his experiments. He did experiments in other subjects, which sound dubious nowadays, subjects like alchemy, but alchemy was, of course, a precursor of chemistry, and in those days, that's where chemistry was. So he, on the one hand, was an experimentalist. On the other hand, he was a theoretician. He constructed theories to explain his experiments and to explain other observations. And he's very famous, of course, for many theories, including his laws of motion, his theory of gravity, which explained planetary motion and optics, and his work on fluids. He was also deeply religious, and in fact, he wrote more about religion than anything else. But I put that in parentheses because that is not the subject that I'm going to be talking about. And thirdly, he was a great mathematician, one of the greatest mathematicians ever, who constructed new areas of mathematics in order, from his point of view, to try and explain the physics, or try and describe the theories. So there's this strange symbiosis, a symbiosis between the experimental and the theoretical side of the subject, and then between the theoretical side and the mathematical side. And it's extremely difficult to convey to people who are not involved in this work what that involves. In particular, mathematics is something which is intangible if you're not immersed in it. But there's a notion that mathematics is beautiful and very important for us to construct models of the physical world. The well-known physicist Eugene Wigner is often quoted as talking about this as the unreasonable effectiveness of mathematics. It's puzzling that big advances in theoretical physics almost always involve the use of elegant mathematics, whatever elegant mathematics means. So let me just talk about that a little bit. The notion that something is elegant is somehow connected with the fact that it's beautiful, but what does it mean to say that you've got beautiful mathematics? Here's an equation which is one of the... Here is an equation which is one of the most beautiful equations in our subject. It's the Dirac equation, which will look like just a scribble to those of you who are not used to looking at mathematical equations. This is the equation that predicts the existence of antimatter and is one of the most important equations in theoretical physics in the 20th century. But it's just squiggles to those of you who don't understand that it's in fact a very beautiful equation. And in a sense, that's analogous to these squiggles here, which are notes on a stave written in the handwriting of Beethoven, which again would not appear to be beautiful to look at, but once you know what they mean, then you understand that they're beautiful. And that's the closest I can think of an analogy to why people who are immersed in this kind of mathematics see beauty in equations. And here's another quote from this time a famous mathematician who was also a theoretical physicist, Poincaré, who said, the mathematician does not study pure mathematics because it is useful. He studies it because he delights in it, and he delights in it because it's beautiful. And that's really the motivation, that mathematicians use for studying mathematics, but it's also the sort of motivation that motivates people in theoretical physics who are looking to try and understand the laws of nature. So let me talk about that. So this is a brief history of physics, from theoretical physics, from the time of Newton onwards, more or less. And the reason I want to show this is to illustrate that we think of progress as something involving unification. When different ideas are unified and can be thought of as different aspects of the same theory, then we think that there's been progress. So let me just point that out in a number of cases. So these characters here, starting perhaps with Copernicus, and then Kepler and Galileo and Newton, transformed our understanding of science by understanding that astronomy, which has to do with things outside the Earth, and physics, which had to do with things happening on Earth, were in fact different aspects of the same subject. So the universality of physical laws emerged around about the 17th century out of these ideas. Somewhat later, the apparently different disciplines of electricity and magnetism were understood to be different aspects of the same fundamental force, which is the electromagnetic force, most notably following the work of Ampere and Faraday and Maxwell. And I put underneath these headings the kind of outcomes that these ideas lead to, because one of the points about talking about this is that the motivation that these people had for undertaking their research was just wonderment at the universe and a desire to understand its laws. But of course, the outcome was that they completely transformed society because the uses to which their research were put eventually led to amazing applications, such as the ones listed here: radio waves, X-rays, microwaves, and so forth. So it's very difficult to predict the outcome of any research if the research is motivated by just the desire to know more about the universe. Another on this list of the history of physics and unification was the work of Einstein at the beginning of the 20th century, where his theory of special relativity led to a unification of the idea of space and the idea of time. Space and time are nowadays thought of as a single object, space-time, and that led again to all sorts of important outcomes. This equation here is probably the only equation I'm going to write in my whole talk, E equals mc squared, simply because you all know it. You may not know what it means. But that's the equation, of course, that underlies the whole of subnuclear physics and has led to all sorts of important developments. And then 10 years later, Einstein again generalized his theory of special relativity to what is called general relativity, and that involved a unification of gravity with mathematical ideas, geometric ideas, and at this point we begin to get to subjects which are much less easy to be intuitive about in giving some general talk. But there is here a unification of the idea that something can be curved, which is geometry, with the idea that that the curvature of space-time is equivalent to, generates a force, or is equivalent to a force, the force of gravity. And this theory, which supplanted Newton's theory of gravity, is one which explains the large-scale features of the universe. So much of what I'm going to say later is explained by understanding how general relativity works. And then, a few years after that, quantum mechanics was finally understood. Quantum mechanics has to do with the microscopic world and the way in which microscopic objects behave. And that was something which began with the work of Planck in 1900 and was finalized by Schrödinger and Heisenberg in 25-26. That was a huge revolution, which I'm going to come back to later in this talk, which transformed our understanding of atomic and subatomic physics. But soon afterwards, That was unified with special relativity, Einstein's theory, and that was unified with special relativity by Dirac, here in Cambridge. And that led immediately to that from that equation, which I showed you before, that led to the prediction of antimatter. And it led on very quickly to a subject known as quantum field theory. So quantum field theory is emerged out of the attempts to unify quantum mechanics and special relativity. The idea was to apply it to a quantum version of electromagnetism, which eventually was successful. But it's in fact, it's become the basic framework for describing all theories, or it became the basic framework for describing all theories of subatomic particle physics. So the theories of the type I'm going to allude to later are all, in some sense, fall under this umbrella of quantum field theory. But the interesting feature is that it took many years between 1928, when Dirac wrote down his equation, and the time when the quantum field theory that describes particle physics was understood. But although it took many years, what happened almost immediately and very unexpectedly was that this apparatus of quantum field theory was understood to be a tool which could be used in many other contexts. So although it was invented for one purpose, it became a tool which is still used. It's the basic tool which is applied to understanding a wide range of physical systems, well away from the context in which it was originally invented. So it became the tool for understanding condensed matter physics, in particular, and fluids, and led to, again, all sorts of developments, none of which any of these people who were working on the theory originally could possibly have predicted. So one of the messages of this talk is that when someone asks you to justify your research with a very concrete application of it, then, well, depending on what sphere of research it is, it's not always the case that you need to justify it beyond its intellectual curiosity. So I've listed a number of times in the history of the development of physics in which there's been a unification of ideas which were apparently from disparate branches of the subject, but this leaves one which has not yet been, which I haven't talked about, and that is, how does one unify quantum mechanics with general relativity? General relativity, remember, has to do with the force of gravity. And this is a problem which was understood to be a problem almost 100 years ago, well, at the time that quantum mechanics was first understood. There seems to be an inconsistency in the structure of quantum mechanics, which has to do with the microscopic world, and the structure of general relativity, which works very well on large scales in astronomy. And so the fact that these amazing achievements of 20th century physics appear to be inconsistent with each other is one of the great challenges to be understood, perhaps in the 21st century, if we're lucky. There's still a lot of the 21st century to go, so maybe that will happen. And there have been lots of ways of attempting to resolve this issue, and the one I'm going to talk about has been the one which has been quite notable over the last 30 years or so, namely string theory. But let me immediately say that string theory is a misnomer, and calling it a theory is very premature, so let's call it string and not yet a theory. It's, in fact, one of the exciting things about the subject is that we don't understand it, and yet at every stage when we understand more and more of it, it looks more and more interesting and motivates us to look further. So that's a very quick background to the history of theoretical physics, to set the scene for the kind of theoretical physics we're talking about. Let me now say a word or two about what it is that is out there that we want to explain. So what are the phenomena that theories of this type might explain? Well, I'm not going to give an exhaustive list, because that would go on for much too long, but the amazing thing is that the very biggest questions of all are the most obvious questions, and those are the ones which, in fact, are probably the most difficult ones to explain. So let me just say what I mean by that by giving a couple of examples. The most obvious example is that when you go outdoors and you look up at the sky, you see this enormous universe. And we all understand the universe is vast. What we may not understand is that its vastness is a puzzle within the context of trying to explain the physics that's going on inside it. In order to illustrate that, let me just give some numbers here. So the visible universe is about 1 trillion kilometers across. That's the universe that we can see from the light that's coming towards us. That's often measured colloquially in light years, so that's a large number of light years. But a light year is not a very natural unit in this subject. There is a natural unit in any attempt to understand the quantum mechanics underlying the smallest processes in nature. There is a natural length scale, and that's the scale called the Planck length. It's made up out of the fundamental constants, which for those of you who are inclined, I've written on the right-hand side. That's Planck's constant, Newton's constant, gravitational constant, and the speed of light. That combination gives you the Planck length, and the point is the Planck length, which is the natural length scale within which to measure length scales in this theoretical, in this kind of theoretical physics, is about 10 to the minus 33 centimeters. So in those units, the size of the universe is truly humongous. So it's about 10 to the 62 Planck lengths across. That's a very large number. When I say that, what I mean is that there's a certain sense in which it's rather more natural when you do your calculations to come up with a number of about 1 or 100 or a few hundred Planck lengths. Coming up with a number like 10 to the power 62 looks extremely unnatural. Hand in hand with that, the universe is very old. The universe we see came from a Big Bang about 13.7 billion years ago. Again, a year is not a very good unit to use, not a very natural unit. The natural unit of time is the time it takes light to travel across one of these Planck distances. And since the light travels very quickly, that's a very short time scale indeed. It's about a few times 10 to the minus 44 seconds. So the universe is extremely old and extremely big. These are huge numbers, but there are other numbers which are extremely puzzling. The particles that we see in nature, the masses of the particles that we see, like the electron and the proton and the neutron inside the atom, are all extraordinarily small when measured in these natural scales. So that hand in hand with the length scale and the time scale, there is a natural sort of quantum scale of mass, which is huge compared to the mass of the particles. So the proton, for example, inside the nucleus of the atom, is about 10 to the minus 19 Planck masses in weight. So that's a tiny number. So any numbers which are either enormously big or enormously small are the ones which are difficult to imagine predicting. There are numbers which would suggest that we live in an untypical universe. And I'm going to come back to that towards the end of the talk. So we live in a very untypical universe, but we know a lot about it, or we think we know a lot about it, from experiments that have been done. And I'm just going to mention a couple of recent and very important experiments. The first is an experiment from the Planck satellite, which measures surveys the whole universe in microwave, and is the latest in a succession of extraordinary experiments which have done this more and more accurately as the years have gone by. And this picture, which I'm not going to spend much time or any time explaining in detail, is a representation of what it sees, which is colored in red and blue to represent hot and cold bits of the universe. And what it's seeing, although that's not at all obvious from this picture, is looking at temperature fluctuations from the radiation that's coming towards us, that has been coming towards us since about 300,000 years after the Big Bang. So this radiation it's looking at is a relic of the Big Bang, is a relic of what the universe looked like shortly after the Big Bang, 300,000 years after the Big Bang, which is about 13.7 billion years ago. And it's got several features which are extraordinary. One of them is that the temperature, although as I say you can't see it from this plot, but what this is showing in fact, is the temperature is amazingly uniform across the whole universe. That far away in that direction, far away in that direction, the temperature is the same to extraordinary accuracy, which means that at some point those two patches had to be very close together. That's one of the extraordinary features. But the other extraordinary feature is that it's not quite uniform. There are fluctuations, and those fluctuations, which are the fact that not everything is the same color, are fluctuations which are understood to have developed later on, following this 300,000 years after the Big Bang period. They developed into the structure that we see in the universe. So although the universe is more or less uniform, because the temperature and all the other properties are more or less uniform across the whole universe, it wasn't quite uniform, and that not quite uniform aspect eventually led to the formation of stars and galaxies and clusters of galaxies. And so this is understood now in amazing detail. So this is one of the amazing experiments. And amongst other things, what has come out of this is confirmation that what we see as matter in the universe, the visible matter, if you like, is only a small fraction of all the matter. So that we understand now that about 83% of all the matter in the universe is made up of stuff that we don't understand. We don't even know what it is. And one of the great questions at the moment, experimentally, is to try and measure phenomena which would tell us what the universe is made of, what this dark matter is. And even more amazingly is that the 68% of all the energy in the universe is not locked up in matter. Matter, remember, is equivalent to energy, because E equals mc squared. But 68% of all the matter, of all the energy in the universe, it comes from an energy associated with empty space. And in general relativity, there is such a phenomenon. But what it leads to is the statement that the universe presently is expanding at an ever-accelerating rate. The universe is blowing itself apart. And that was a very surprising result of an experiment done initially about getting on for 20 years ago, or 18 years ago, but it's confirmed by all this recent data. These two facts are astonishing. I mean, there was a time in our history when we thought the Earth was at the center of the universe, and then Copernicus came along and said that no, the Earth is not at the center, the sun is at the center. And then we understood more that the sun is not at the center of the universe, but it's a star in a galaxy, and that galaxy is something we can see, and that galaxy may be important, or at least galaxies in general may be. But now we have an idea, we've got these ideas which are almost of the same significance as Copernicus's idea. That not only are we not at the center of the universe, we don't even know what the universe is made of. And so there's a lot to learn. So sticking to the theme of the universe, what I want to do now is start with the very big, with the whole universe, and then come down to smaller things. So let me just talk about the evolution of the universe since the Big Bang. So the Big Bang happened about 13.7 billion years ago, and the whole of what we now call the universe, the visible universe, was at that point an unbelievably small object. Discussing it in detail at the earliest times is something that we can't really do with a great deal of certainty. But the earliest times I'm talking about now, I've written the Planck time here. So going back before the Planck time may or may not make any sense, and there are all sorts of speculations about it. But what is impressive is that the history of what happened after that time is pretty well pinned down. So if I plot the time since the Big Bang, at the time of the Big Bang, the universe was extremely hot. It then expanded and cooled down. And what is now believed with great certainty, although it's still controversial, is that very shortly, at some very early time, this minuscule Planck-sized universe expanded dramatically in almost no time at all to something which is roughly the size of a grapefruit. So that was some initial period of what is called inflation, which accounts, that actually accounts for the homogeneity of the universe, and it also predicts something about the inhomogeneity, the variation of the microwave background that I was talking about earlier, which was necessary to get the galaxies. Then a very short time after that, the universe had cooled down sufficiently that the kinds of energies that the particles, that the stuff in the universe had, were the kinds of energies that can be recreated on Earth at the LHC. So these timescales are astonishingly small, but of course you shouldn't be thinking in seconds. I plotted seconds there. What you should be thinking of is Planck times. So although 10 to the minus 12 seconds is a very small fraction of a second, it is a very large number of Planck times. And the Planck time is a natural time on which things happen in this kind of physics. So a lot happens in a very small number of seconds. So after about 1/100,000th of a second, particles like the protons started to form. And after a few minutes, the nuclei formed. And then a long time later, the universe was cool enough that atoms could form, and when atoms form, the radiation that was in equilibrium with these particles decoupled, and it's that radiation that we're seeing in those in the picture I showed you earlier. And then a long time after that, but still a very short time in the history of the universe, about a few 100 million years, stars suddenly lit up, and the universe came alight, I should say. And then proto-galaxies form, planets around the galaxies developed life, and after 13.7 billion years, here we are. The universe had cooled down from being very hot to being almost at absolute zero. And then what we now see is that the initial inflation which tapered off to a steady expansion, is now gone to another accelerating phase. So that's the history of the universe until we formed, but now here we are on Earth in Cambridge, and everything I said, most of what I said before depended on understanding how gravity affects the evolution of the universe. But once you're talking about things on the tabletop, or buildings, or objects on Earth, it's more important to understand how other forces work. So there are electric and magnetic forces that hold atoms together and make up molecules, and so the force of electromagnetism is important, because that's much, much stronger than gravity. So understanding electromagnetism was a crucial ingredient in understanding modern physics, and in order to get to where I want to go to, let me just say a little word about the particles that make up the atom. So the first elementary particle that was discovered was the electron, discovered here again in Cambridge, by J.J. Thomson in 1897. And this was a huge development, simply because people previously had no proof that there were such things. There had been arguments about whether there was a corpuscular level of matter or whether there wasn't. And so people, of course, asked, what on earth is this small particle that carries an electric charge? And it looked, to all intents and purposes, as far as you could measure anything, as if it was a point. But it was obvious that it couldn't be a point, because there's an obvious inconsistency in having a point which carries electric charge. And if any of you have ever seen well, you could ask the same question about a magnet. The lines of force meeting at the north or south pole of a magnet, well, for a point electric charge, the electric field lines all meet at one point, and that means that mathematically there's an inconsistency. It means that there's an infinite energy density at that point. So people argued a great deal about what you do with this point-like object, and people tried very hard to produce theories in which the fundamental particles were not points, but they were extended objects. But they failed at that time. And they failed at that time partly because they didn't really have the mathematical apparatus to understand how to construct a theory in which the electron was not a point. And in a certain sense, that's what string theory is. It's a way of circumventing some of the problems associated with point-like particles. But anyway, other ways were found of dealing with such point-like problems, and almost all of 20th century physics went ahead assuming that the fundamental particles were points. I mean, nobody really believed they were points, but nevertheless, since they didn't really know how to avoid the problems, they shoved them under a rug, and they managed to make predictions which didn't depend on their point-like nature. And this led to the whole fabulous number of discoveries in atomic and nuclear and particle physics in the 20th century. All of these subnuclear phenomena fit in with the ideas of quantum theory, which I mentioned earlier. And again, this is a subject which is extremely difficult to be intuitive about and very difficult to describe in words. In fact, some of the problems or the perceived problems in quantum theory have to do with the fact that we would like to describe certain aspects of it in words when in fact they probably can't be put into words. So in some sense, quantum mechanics is anti-common sense. It embodies, I'm going to say very little about quantum theory other than the fact that it embodies this uncertainty principle, which roughly speaking says that certain aspects or properties of objects that we are used to thinking of as being simultaneously properties of an object cannot be assigned to that object in quantum mechanics. For example, you cannot say precisely where an object is and how fast it's going. Those are two qualities that are incommensurate. The more precisely you know where it is, the less precisely you know how fast it's going, and therefore what its energy is. Roughly speaking, that means that things are fuzzy at the subatomic scale. Even though things are fuzzy and it's difficult to make simultaneous measurements of things that you thought you could measure, it is an extraordinarily accurately tested theory, and it's probably the most accurately tested theory in any branch of science. But the fact that you can't talk about it very easily also motivates people, often philosophers, to argue about what it means. Physicists also argue about what it means, but they don't. They then go and use it anyway without worrying too much about it. So the quantum mechanics is needed to describe the atom. The atom has a nucleus with electrons going around it, as you all know. The electromagnetic force holds the electron around the nucleus. The nucleus itself contains protons and neutrons. The protons and neutrons themselves are made of other particles called quarks. And these quarks are very tightly bound to each other. They cannot be seen individually. You can't take a quark out of a proton. But protons and neutrons are made of quarks. And they're held together by this so-called strong force. So there are fundamental particles. The word fundamental particle is used to refer to particles. In this case, the electron and the quarks are fundamental. The proton and the neutron are not fundamental. They're made of quarks. But the electron and quarks, which we now have a beautiful theory to describe, are described in that theory as being point-like objects. So the fundamental particles are in the theory that describes how the quarks bind together and how the electrons behave, describes the particles as being point-like. And then there are a number of other forces, other particles and forces, and this whole structure has been arrived at by a fantastic series of experiments over many years in accelerator laboratories on Earth, and it's led to the formulation of what amounts to a more or less complete description of all of the particles and all of the forces. It's called the Standard Model. So the Standard Model uses as its tool the quantum field theory, which I talked about earlier. So the reason I mentioned quantum field theory earlier was so that I can now refer back to it and say that the Standard Model is built up from different kinds of quantum field theories, which are very well understood, very beautiful, mathematically beautiful theories, and it accounts for just about everything that has ever been measured in accelerator laboratories. And in fact, you could summarize the Standard Model by a table which, in some impressionistic sense, is meant to remind you of the Mendeleev table of the elements, because it plays that kind of role in particle physics. It's a list of all the known particles. So I'm not going to go through the list, it's not worth it at this point, but there are particles, the quarks are up here, the electron is down here, and it has a partner particle called the neutrino, and then there are 3 copies of the electron called the muon and the tau, and they're neutrinos. And then there's a whole other set of particles called bosons, one of which is the photon, which is associated with the electromagnetic field, but then these other particles are associated with the other forces. And then finally, there is this guy down here called the Higgs particle, and a couple of years ago I would have said it was very much hoped that this would be discovered, but actually it says it on the, it says yet to be confirmed. This is an old slide, but I've changed this in blue is new. So a couple of years ago, the particle was, with much media publicity, discovered at CERN, and that finally tied up the whole of the Standard Model. So here's a model which contains everything we want to know, which is very much like the periodic table and therefore has an elegance about it. But in a certain sense, it's unsatisfactory. Nobody working in this field is satisfied with that. They're extremely happy that this is the way things are, that we understand how things are put together, but there are aspects of it which we don't like. And one problem is that it works too well. As I said, it more or less explains everything we know in particle physics. But we want to go beyond it, and so we'd like some evidence that there is something beyond it. So one thing we want is some experimental signal that the Standard Model isn't the whole story. And there are a few such signals, but they are very few, and we would like to understand such signals much better. The reason we want to go beyond it is, well, there are 2 reasons that I feel are important. One is just an aesthetic question. The model, the Standard Model works beautifully, but it's sort of arbitrary. You have to put in which species of particles you're describing, and you have to put in their masses, and you have to put in some properties of the forces, and then out comes a huge number of predictions which work. But in a sense, it's these arbitrary features that we would like to predict with a more fundamental model. But the second problem is, in many senses, the worst problem, which is what is the problem that motivates most of us, which is that the Standard Model says nothing at all about the force which is, in a sense, the most familiar force of all, even though it's the weakest force, which is the force of gravity. So the fact is, you can get away without describing the force of gravity when you do experiments in the lab, because gravity is so weak between individual particles. But of course, we feel gravity on Earth because the Earth is so large, and furthermore, cosmological bodies feel the force of gravity because they are so large. And the whole evolution of the universe, as I described earlier, depends on understanding the force of gravity in the large scale. But since the universe was initially minuscule, we need to understand how gravity works for minuscule objects. And that there is an intrinsic problem in understanding that, because there is an apparent inconsistency. If you treat general relativity or gravity in the standard way, you get nonsense, which I'll illustrate in a couple of minutes. So finally, at last, I'm turning to string theory. I've given you a very long introduction to set the background. The idea, the motivating feature of string theory is that it appears to have the possibility, at least, of resolving these issues that I just mentioned to do with the Standard Model. Now, string theory has some daunting technical features, but it's based on what is, in fact, an alarmingly simple premise. You have to, the way string theory emerged historically, well, the way it emerged historically a long time ago is an interesting but complicated story. But let me simply say that the way string theory is formulated in its most basic way is that you say that instead of particles being point-like, so here's a picture of a point, so you can see that a point has no structure, but a string can vibrate. So instead of particles being points, What you're supposed to think of is a string-like object which can vibrate, and just like a violin string or a musical string, it can vibrate in any one of a number of harmonics, in fact an infinite number of different harmonics or different notes, and each harmonic corresponds to a different frequency, and a different frequency corresponds to a different energy, and therefore the different harmonics are identified with states or particles with different energies or masses. So the different particles that we see in nature are in some, this is a very schematic description, of course, but roughly speaking, you're supposed to think of the particles as being associated with the modes of vibration of a string. So in that sense, this gives a very unified description of particle physics. That's what we're hoping for. So I note the word potentially here, because this is not something which has been worked out in detail, but this is one of the hopes of the theory, is that we could explain the different kinds of particles, the quarks, the electrons, neutrinos, and so on, as being different notes or different harmonics on a single kind of object, a string. And therefore, we would hope that we could understand properties of the standard model. But perhaps even more strikingly, as far as someone who is a theoretical physicist is concerned, the theory appears to contain gravity in a way that's consistent with quantum mechanics, and contain gravity unified with the other forces. Remember, quantum mechanics didn't seem to be consistent with gravity. But it seems that the fact that strings are points rather than, strings are not points, avoids the problems with infinities in a way which is easy to demonstrate mathematically, but it is not easy to understand in any, it's easy to illustrate mathematically in a rather superficial way, but the deep meaning of it is something that we don't yet have full intuition about. Let me illustrate that with a couple of small animated sequences, rather amateur animations. So when we talk about particles in particle physics, we tend to talk about what happens when they hit each other and bounce off each other. So in the simplest possible example of that, two point particles join together, move along, and then split apart. And that's part of the description of the scattering of particles. And if I trace out the lines if I draw the lines that these particles trace out as they move, you get a diagram. And this diagram is what is called a Feynman diagram. And although that's meaningless to you until you know the rules, there are rules associated with these lines and the nodes for calculating the probability of these particles, of incoming particles, ending up in a particular final state. However, in ordinary point-particle theories, which means quantum field theory, the existence of point-like places where these lines join and split leads to problems. It can lead to problems. It doesn't lead to problems in the standard model. Well, it leads to problems which can be swept under the rug and ignored, which is what I was saying earlier. But when you come to a theory containing gravity, these problems give you nonsensical answers. And a quantum field theory of gravity seems almost certainly to be ill-defined because of this. Compare that with what happens in string theory. In string theory, two strings come along instead of points, and they join, but they join in a very geometrical way. They join smoothly. So that a string sweeps out a surface, and this surface is the analog of the Feynman diagram I just drew, but this surface has no points on it, no marked nodes. And that actually results in the statement that this theory has no problem, doesn't have what are in fact short distance problems that quantum field theory has. I thought I'd throw these pictures in because even though you may not, there's no hope that you'd understand them in any detail, it's just to show that there's a pictorial way of seeing what the key difference is between string theory and the older theories. There were some odd things about string theory. So, for example, you can't fiddle around with the dimension of space and time. You have to accept what the theory tells you, and it tells you, in its simplest version, that there are 10 dimensions. 10 is more than you're familiar with. We're used to there being 3 directions in space, and then time is a 4th. So there are 6 that you're not familiar with. But luckily, in a theory that contains gravity, there is a notion that dimensions can curl up under the gravitational force and in some sense become small and unobservable. So you can get lots of curvature in directions that are difficult to imagine, but you can write down mathematically. There are directions where if you try to point your finger, you get back to where you start before your finger gets anywhere. So in some sense, they're unobservably small. So you need 6. It had better be true that the world we live in, if it's described by string theory, has 6 curled up dimensions that we don't really see, and 3 ordinary space and time. This is the second equation in my talk, but that one you can understand. Now, one aspect of this, which is a problem, if you view it as a problem, is that there are huge numbers of different ways in which these 6 dimensions can curl up. I should say this has spawned a whole branch of mathematics, or several branches of mathematics. In fact, one of the things that is astonishing about string theory is its interaction with mathematics. There has been a tremendous coming together of branches of mathematics and string theory, and they feed off each other, and they have produced some remarkable new results, and this is one of them. So I've just thrown in some names here. Mirror symmetry, Calabi-Yau spaces, conformal field theory. These are areas of mathematics now, but they had their genesis in string theory, and they have a lot to do with the way in which dimensions can curl up. The problem, if you see it as a problem, is that every different way in which the 6 dimensions curl up leads to a theory which now only has 4 dimensions, but it's a different theory for each one of these different ways that the dimensions curl up. So that what you see in physics looks very different. You see a different kind of universe depending on which of these different solutions to the theory you take. And that's called, by some people, that's thought of as being a problem, by many people, because we don't know which of these solutions describes our universe. So the set of all possible solutions has come to be called the string landscape. There's a landscape of solutions. We would like to know which of them describes our universe, but there's no way at the moment of deciding that unambiguously. It might be that we're missing a principle which tells us that one of these, or some class of these curled up solutions is the correct one. But there's no real way of understanding that at the moment because we don't really understand string theory. String theory is incomplete. And I want to say a few words about that, the last part of my talk. We know that it's an approximation to a complete theory, but in the complete theory, there are very general reasons for understanding that it isn't enough to talk about a string wiggling as it moves through space. Space itself has to be stringy in some sense. In a theory which involves quantum mechanics and space-time and general relativity, we know that space and time has to be dynamical in a way which is even more difficult to describe, because without using mathematical language, it's almost impossible to imagine what that means. But whatever that means, it means that we have to have a theory in which space and time are emergent, that our equations will determine properties of space and time, and in such a space-time of this nature, we could call quantum space-time, but we don't understand it. But not understanding it doesn't stop us giving it a name, and this has come to this extension of string theory that includes the quantum mechanical nature of space-time, even though we don't know what it is called M theory, where M could stand for a number of different things, and that's one of the mysteries of the subject. So we don't understand what it is, but in the search for trying to understand it, all sorts of very interesting and very speculative developments have taken place. These are largely based on the observation that strings are not the only extended objects in string theory. So strings are extended objects, but when you understand the theory in more detail, you understand that there's a whole collection of other extended objects. The prototype being things which are familiar in general relativity anyway, which are black holes. But there are generalizations or extensions of black holes, which are called black membranes or black p-branes. These are, a black hole in a sense is a localized lump of energy localized around a point, whereas a black membrane or a black p-brane is more like some sort of soap bubble where the energy density is localized on a surface. But since we've got more than 4 dimensions, these P there can be, a membrane is a two-dimensional, a soap bubble is two-dimensional, but you can get higher dimensional objects in string theory. And understanding these objects seems to have given a rise to an understanding of all sorts of interesting issues. And in particular, one aspect that has been studied enormously, because it's such an important test of our understanding of quantum gravity, is trying to understand quantum properties of black holes. This subject, of course, was initiated in the mid-70s, in 74, by Stephen Hawking's extraordinary work. And ever since then, people have been puzzled by aspects of the quantum properties of black holes that I haven't got time to understand, but to talk about. But in particular, he raised, I certainly also don't understand it. He, at that time, or in 70, shortly after that, raised an extremely provocative question about what happens. In 74, he understood that black holes, which up to that time had been thought of as objects that into which things fall, but things don't get out, he understood that in the context of quantum theory, things do get out of black holes. They radiate. And the question is, if things fall in and then radiate out, the paradox was that the stuff that comes out seems to be completely uncorrelated with the stuff that went in. In other words, there's a loss of information. And that loss of information was a paradox because that indicates a breakdown of some sacred principles that go into quantum theory. So people have discussed that in great deal ever since then, and the fact that we can now construct some sort of black holes in string theory is the first time that we've had a consistent way of talking about quantum gravity. So we can construct black holes, at least try to construct black holes in string theory, and try and answer that question, is there really a loss of information? And the statement is, at the moment, we don't know. A couple of years ago, I think we would have said, yes, it's been resolved, but actually, in the meantime, people have pointed out flaws in that argument. And currently, this is one of the most stimulating things that people are discussing or arguing about. What happens, in particular, there's a horizon around a black hole, and there's a question about what happens if you fall through that horizon. And there's a possibility that there are bizarre effects which are not yet understood. A second topic that's been talked about a lot is something called the multiverse. So again, this is very speculative. The multiverse is something which I could give the subtitle to making a virtue of the string landscape. Remember, the string landscape is a statement that there are huge numbers, enormous numbers, of possible string solutions to string theory, each one of which corresponds to a distinct possible universe. Each one would have its own set of physical laws and would evolve in a different way. And we don't know how to decide which one we live in. But according to the people who advocate this approach, one could do the following. Most of the universes that would come out of string theory, most of these solutions, would not be universes that we could live in. They're universes which would either collapse very quickly in a Planck time, and therefore would never evolve into anything that would produce galaxies, stars, galaxies, or planets, or they would blow themselves apart very quickly, and therefore also not produce anything that could support the Earth that we live in. We live, as I said earlier, and this is coming right back to the beginning, we live in a universe that is extraordinarily special. And the question about why it's special is what's being addressed here. And according to this way of thinking, it's not that the universe is particularly special, it's the fact that we live in the universe that is special. In order for us to be thinking about the universe, it has to be one of the universes, one of the very small fraction of these universes, which does live long enough to evolve galaxies, planets, life, and this place, in order for us to be thinking about it. So the fact that we're here, even though it's a small, well, the claim is that there's a small probability, we just have to be in such a universe. So one way of approaching the question about why the universe is so enormous which is the same question, is to say, well, there are many universes in which just disappear before they become enormous, and we don't live in those because they don't support life. However, and people try to give probability arguments for this on this issue, but the problem is that we live in one particular universe, and we only have a sample of one, and so whether or not it's meaningful to talk about the probability of us living in such a universe is debatable, or it's certainly controversial. This is the anthropic viewpoint. An alternative viewpoint is that we should first understand the theory better before trying to understand the statistics of its solutions. So those are just a couple of examples of some rather speculative but nevertheless extremely interesting developments that are taking place. From my point of view, though, the most interesting things that are happening have to do with something different, which is the fact that string theory, which was invented for one purpose, it actually was invented for a purpose I haven't even discussed originally, moved on to try and was developed into a theory that was supposed to describe the fundamental particles and their forces, has in recent years turned to a somewhat different kind of issue. It looks as if string theory could be a new mathematical tool for discussing physics for discussing all sorts of different issues in physics. Rather like quantum field theory, remember, was invented for one purpose, but rapidly became a tool for discussing a wide variety of other issues. And this is based on a principle which we believe is a general principle, but string theory seems to illustrate it most clearly, and that's been called holography by analogy with the principle of holography in optics. And that's the statement I'm about to make will sound bizarre, but it seems to be something which is, well, it is something which is built into particular examples within string theory. And that is that if you take a theory, you try to describe quantum gravity in general, d plus 1 dimensions. So d for us would be 3 if we were in 4 dimensions, but let me call it d plus 1. It turns out that the physics of gravity in d plus 1 dimensions is the same, in at least in certain very special cases, as the physics of a theory which doesn't have any gravity. In other words, a theory to do with condensed matter, say, in the lab, but a theory in d dimension, one less dimension. So it's a non-gravitational theory. And so there's this relationship between gravity on the one hand and non-gravity on the other hand, and that's led to all sorts of very interesting developments, none of which have been rigorously understood yet, but all of which look interesting. So let me just illustrate that with a little picture. So let me illustrate it when d is 4. So the gravity theory is in 5 dimensions, and this is a symbolic picture of something which has a very precise mathematical meaning. Here is a space with, think of it as a ball of some sort, which has a boundary. The surface of the ball is a boundary. So the ball is like the 5 dimensions, the interior of the ball, and the surface of the ball is 4-dimensional. So the interior is going to be described by string theory. Now it turns out if you drop a black hole into this ball, the black holes radiate because of what Stephen Hawking taught us all those years ago, and so you heat the whole interior up with, in this case, stringy radiation, and so the surface becomes hot. And it turns out that the physics that describes a black hole in 5 dimensions also describes something which is not a gravitational theory at all in 4 dimensions on the surface of the ball. It's a condensed matter theory. So there's been an enormous coming together of people who are interested in this kind of aspect of string theory and certain condensed matter theorists who don't all agree that this is the right way to approach condensed matter, but those who do are very enthusiastic about this, and various problems in condensed matter physics have been attacked in this way. I want to show one transparency which illustrates a situation in which this has actually proved very useful experimentally. There's an experiment which has been going on at Brookhaven for many years and is now being repeated is repeated at the LHC, in CERN at higher energies, in which you collide ions, nuclei of gold atoms, they're heavy ions. They collide at enormous energies. They form, experimentalists look at these things and they describe what it forms as a plasma, a fireball, of this very hot nuclear matter, which then rapidly decays into very many particles, which is what you see in this picture. These particles are protons, neutrons, and other particles. Whilst this plasma is in existence for that very short time, it behaves like a fluid. And that fluid is like the fluid on the boundary of the picture I just drew. And it can be described, the properties of that fluid, in particular its viscosity, its shear viscosity, can be described in terms of as if you were looking at a system which had a black hole in it in one extra dimension. So instead of being in 3 dimensions, 3 space dimensions, it's in 4 dimensions. And that explanation of it turns out the viscosity is remarkably small. And there is no standard explanation of why it's so small, but it comes out rather naturally from this point of view. So that's a rather interesting one of many interesting new systems to which string theory may be applied. So let me finally say that, just summarize by saying that string theory is very exciting for those in it because it combines the physical principles that you would like to have in a fundamental theory, namely quantum mechanics, general relativity, quantum field theory. And it therefore addresses some of the central problems in particle physics and in cosmology. But it's an unfinished project. There hasn't been yet a detailed description of the standard model in terms of string theory. There have been ideas about how to do it, including ideas based on the anthropic ideas that I mentioned earlier. But we're some way, I suspect, from really understanding how to describe particle physics in terms of string theory. And there are all sorts of experimental results that we would like to see arrive before we really understand what we were doing. And then finally, let me say that, I just reiterate what I was saying before, that actually, even more strikingly, I think, the theory has become a tool for tackling a wider variety of problems. The heavy ion collisions I mentioned, high temperature superconductivity is another challenging subject in condensed matter physics. And string theory at least looks like it's providing insights into those problems, even if it hasn't yet described them in detail. What I haven't talked about is almost certainly its most remarkable feature is its interplay with mathematics. I mentioned it, but I haven't really described it. So let me just end by saying that that string theory has evolved in the past in unforeseen ways in which I didn't even mention in this talk. And each time you think you've understood something, it seems to tell you something else that you hadn't even thought that it was a question. So it's sort of got a will of its own. And in any case, it's got such a beautiful mathematical structure, and it's almost certainly going to tell us something that we would like to understand. Thank you.